Welcome children, welcome to another chemistry class. In this video, we are going to have a quick revision, a rapid revision on chapter 3. We are going to have a quick revision on unit 3, classification of elements and periodicity in properties. All of you know it's a very simple, small chapter, but definitely one question we can expect for all the competitive examinations. And a quick review on this chapter itself will make you enabled to answer that question, right? Strictly, you need to go through NCERT and identify the valid points to revise from the very small chapter from the entire 11th and 12th standard chemistry. Okay, let's go through. See, the chapter starts with the historical aspects of development of periodic table. All of you know, the periodic classification basically historically starts from the person Lavoisier, who classified, father of modern chemistry, Antoine Lavoisier, who classified then available some 30-35 elements into metals and non-metals. That is the starting point. Lavoisier classified elements into metals and non-metals. So we can start from that point. Lavoisier classified elements into metals and non-metals. That was not a systematic classification, just categorizing, we can say. Then another important contribution, all these are historical aspects. Another important contribution came from Dobereiner. You might have heard about Dobereiner. Dobereiner's law of triads. Law of triads. He grouped the elements into three elements as a group. That is why it is called triads. Triads. Dobereiner's triads. I'm sure all of you know this. For example, if you take a lithium, sodium, potassium, which is a triad, chlorine, bromine, iodine, which is a triad, he suggested the properties of the middle element is found to be the average of 1 and 3. That is law of triads, explained by Dobereiner. That is still explained. All these things are explained in the NCERT. So Lavoisier explaining metals and non-metals, Dobereiner's triads, certain elements grouped into three elements as a group, law of triads, right? Then several other names, Lothar-Meyer, sometimes you might have heard about Lothar-Meyer contribution. Lothar-Meyer tried to explain the periodicity in such a way that he was able to plot a graph taking atomic volume, melting point, boiling point, etc. versus atomic weight. He was able to find out some periodicity in that context. Lothar-Meyer. Then who else? Deschamps-Cortis. Deschamps-Cortis. He was able to categorize the elements and was able to align the periodic elements, periodicity of elements in a cylindrical format. You might have heard about Deschamps-Cortis. Then who else? All these are some important names that is coming to several contributions we can see from the historical aspect. But we can see the modern systematic periodic table was explained by, all of you know, the father of modern periodic table, Dmitri Mendeleev. That is the person who need to be remembered in this context. Dmitri Mendeleev. Mendeleev's periodic table, and he was able to explain a law, Mendeleev's periodic law, in which he suggested the periodic properties, the repetitive periodic properties of an elements are a function of the periodic physical and chemical properties of elements are a periodic function of their atomic weight. And he tabulated, first of all, a tabulated arrangement of periodic table was done by Dmitri Mendeleev, a great personality. who arranged the periodic table in the order of atomic weight. And there was a proposed law also, Mendeleev periodic law. The physical and the chemical properties of elements are found to be a periodic function of atomic weight, and based on which the tabulated arrangement came, Mendeleev's periodic table. Right? There was a lot of exemptions were also there. He was able to make some changes in the periodic table when he tried to arrange the elements in the atomic weight. He was unable to order exactly because there was some fluctuations, some changes, and that also you may be know. And moreover, he left some blank spaces in the periodic table. He was unable to place certain elements in the correct order. He put some blank spaces. I hope you remember ICA aluminium, the element which he named ICA aluminium, ICA silicon, etc. After aluminium, below aluminium, he put some blank space. After silicon, he put some blank space, gave the name ICA aluminium, ICA silicon. And when somebody asked, sir, why you do this? He answered, I have no elements now available which can be placed there. Probably later on you are going to discover a new element which can be put there. That was his sense of periodicity. And not simply commenting like this, he was able to predict the properties of those unknown elements. Think about that. And later on, when gallium was discovered, which was so named by him, ICA aluminium. Later on, when germanium was discovered, which he has named as ICA silicon. When later on gallium, germanium discovered, most of the properties he predicted came almost correct. He made a comment, gallium, when you take, the element which you're going to take in the hands, it will melt. The melting point of gallium is as low as some 30-31 degrees Celsius, which is below the body temperature, and it will melt. So many properties he predicted came perfect. That is the importance of the innovative kind of approach which Dmitry Mendeleev, who made on categorizing classification of elements. But the modern periodic law was explained by, all of you know, Henry Moseley. Henry Moseley explained the modern periodic law. Henry Moseley explained modern periodic law. He conducted so many experiments, various experiments with various materials using X-ray analysis. And during his experiment and his experimental studies, which are quoted in the textbook, there was a question for the latest JEE examination. The relationship for frequency of X-ray used versus atomic number. It is there in the NCERT. Frequency versus frequency of X-ray versus root of Z. He made some plot and analysis. And that was a question for latest JEE mains examination. Nu versus Z, when plotted a graph, get a straight line where Z power is given as X. What is X? Very simple. Nu versus root Z. X means it is half root of X, root of Z, root of atomic number. So that studies straight away from NCERT, straight away it came for the JEE examination. This is Moseley's studies, based on which he modified what Dmitry Mendeleev said. The physical and chemical properties of elements are periodic function of atomic weight. What Mendeleev said, he made modification. The physical and chemical properties of elements are a periodic function of atomic, not atomic weight, but atomic number, based on which again several modifications happened, several scientists contributed, and now we have the modern periodic table, the long form of periodic table that we handle now. These are the historic aspects of development of periodic table, which you can find from the initial portions of NCERT. All these initial portion referring those area. Law of triads. Triads explanation you can find in table 3.1. Contribution by Lothar Meyer. Contribution by Dishan Cortes. Newland's, one important point we missed, historical aspect. Newland's law of octaves. Newland's law of octaves. That was an interesting observation. He categorized elements in such a way that he said the properties of eighth element found to be a repetition of the first. Properties of eighth element found to be a repetition of the first. That is still available if you know, if you took the look at the modern periodic table. If we start from say lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Noble gases were not known at that time. So fluorine, neon we will omit. Then it is sodium, then magnesium, then aluminium. If it go like this, you see, starting from lithium, 1, 2, 3, 4, 5, 6, 7, 8. Eighth element found to be the property repetition of the first. And he compared this observation with the musical note. All of you know, musical note. The seventh note is a repetition of the first note on a higher pitch, like that. That is Newland's law of octaves. If you start from say boron, 1, 2, 3, 4, 5, 6, 7, 8th element aluminium, repeating its property with the boron, like that. It is Newland's law of octaves that we missed during the explanation of the historical aspects. Anyway, all these historical aspects landing on the modern long form of periodic table, which is explained over here, which you can find. That is Mendeleev's periodic law. That is contribution of Mendeleev, Ica, aluminium, Ica, silicon, etc. These are the table 3.3. This is the prediction done by Mendeleev regarding the undiscovered elements, so-called Ica, aluminium, Ica, silicon, etc. This is Mendeleev's periodic table. We don't have to give much importance because that is not what we deal nowadays, and the questions we are not expecting from that. And this is what the area which I was highlighting earlier, the Henry Moseley's observation, which came for the latest JEE examination. This part of the textbook. In 1913, English physicist Henry Moseley observed regularities and characteristics of X-ray spectra of elements. A plot of root nu versus atomic number. I think I have written opposite. Yes, it is root nu versus atomic number. Root of frequency versus atomic number. And what was the question? Nu raised to x versus z got a straight line. What is x? Simple. Direct question from the textbook, but based on an experimental observation quoted as a historical fact. A question came for the latest JEE exam. Similarly, many times for the direct picked question from NCERT coming for Neet and other competitive exams. So, such area. Then, modern periodic law, physical and chemical properties of elements are a function of atomic number. These ideas and modern periodic table. About groups, the periods, we will discuss about that. Then, this is the modern periodic table. We will go through the modern periodic table, long form of periodic table. We need to have a straight review of this periodic table and the arrangement of elements. All of us know. See, there are horizontal arrangement of elements, and you can see hydrogen put separately. Even Mendeleev made a comment. I never thought of starting periodicity from hydrogen. That is still valid. Hydrogen has no exact space in the periodic table. It is put separately. So there are horizontal rows. We call it as groups. There are periods. There are 7 periods in the periodic table. Horizontal rows are called periods, 7 periods. And there are vertical columns, 18 vertical columns called groups. All of us know, right? And the elements are classified into S block elements. It is applicable to quantum mechanical aspects. S block elements, P block elements, D block elements, and F block elements. This is the modern arrangement of long form of periodic table. See, elements are arranged in the atomic number order: hydrogen, helium, lithium, beryllium, boron, carbon, like that, in the regular order of atomic number. When we arrange like that, according to the properties, we get the elements. Still, the inner transition elements, F block elements, doesn't find a proper place in the periodic table. There are certain disadvantages even in the long form of periodic table. Okay, so it is categorized into S block elements. This is called the S block elements. Alkali metals: lithium, sodium, potassium, rubidium, cesium, francium, radioactive francium. Alkaline earth metal: beryllium, magnesium, calcium, strontium, barium, radium. Group 2, alkaline earth metal. Then group 13 to 18, P block elements: boron, aluminium, gallium, indium, thallium, and the newly named 113, nihonium. Group 14, carbon, silicon, germanium, tin, lead, and 114, new element, flerovium. Then 15th group, nitrogen, phosphorus, arsenic, antimony, bismuth, new element, moscovium. All elements named, approved with their new name. Then 16th group, oxygen, sulfur, selenium, tellurium, polonium, livermorium, new element. Fluorine, chlorine, bromine, iodine, astatine, tennessine, new element. And noble gases, including the new element organism, right? So, alkali metals, because they are strong alkalis. Alkaline earth metals, they are also alkalis, but not like group 1, lesser character, found in earth crust. Group 13, boron family, also called aluminium family. Carbon family, nitrogen family called nicogens. Nicogens, derived from the term nicomic, suffocating compounds like ammonia, phosphine, etc. Nicogens. Oxygen family called chalcogens, related to chalcopyrites. Halogens, salt forming compounds. Halogens, the most electronegative elements in the periodic table. Halogens, the most electropositive elements in the periodic table. Alkali metals. And inert gases, ideal gases, inert gases, right? And then D block elements. D block elements, mainly 3 series of elements. We learn D block elements in a series wise. 3D series, first transition series from scandium to zinc, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, continuous numbering. 3D series, first transition series, we need to by heart it. Then second transition series, 4D series, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium, continuous numbering. While the third series, that is 5D series, starting from 57 lanthanum, after 57, 58 is not here, we know it is going to 58 cerium. 58 cerium to 71 lutetium. Available in inner transition elements, F block elements, put separately. Where in F block elements, we know there is a gradual decrease in the atomic size, the so-called lanthanoid contraction, due to poor shielding effect of d-f orbital electrons. There is lanthanoid contraction. And this here occurs, lanthanoid contraction, very famous phenomenon. We are going to discuss about that in many times later on also. After 71, we come to hafnium 72, 73 tantalum, tungsten, hope you know, tungsten, high melting metal. Tungsten has got high melting point and high resistance also. Rhenium, osmium, densest element in the periodic table. Osmium, iridium are tight competitor, densest element in the periodic table. Platinum, gold, mercury, and this is new series. We don't study about the chemistry of these artificial elements. Anyway, it is starting from 89 actinium and 90 thorium is available here. After this, 90 thorium up to 103 lawrencium available as actinoid series. This is lanthanoid series and this is actinoid series. Right? So this is about the various elements available in the periodic table. S block elements having a general electronic configuration. S block elements having a general electronic configuration. there is an inner noble gas core with the NS1 to 2. NS1 here, NS2 here. All of you know. Coming to P block elements, there is a general noble gas inner core with the NS2, NP1 to 6. 1 to 6. NP1, NP2, NP3, NP4, NP5, NP6. While FD block elements, we have a noble gas core with the N-1, D1 to 10, NS1 to 2. Exemptionally, it can be NS0 also. NS0 also, like palladium, it is S0. It can be rarely like that also. So noble gas core N-1 D 1 to 10 NS1 to 2. So here the electronic filling is happening in the penultimate D orbital. Here the configuration happens in the valence S orbital. Here the configuration happens in the valence P orbital. Here the configuration happens in the penultimate D orbital. Coming to F block elements, it is again a noble gas core with the N-2, F1 to 14, N-1, D0 to 1, NS2. The configuration is happening here. It is happening in N-2. That means pre-penultimate, anti-penultimate shell. It is happening in anti-penultimate F orbital. Here configuration end up in valence S orbital. Here configuration end up in valence P orbital. Here configuration end up in valence, penultimate D orbital. Here configuration end up in pre-penultimate, anti-penultimate F orbital. Right? This is the overall review of the long form of periodic table. S block, P block, D block, F block. S block, all pure metals, highly electropositive. P block contain all varieties. There are non-metals, there are non-metals, there are metalloids, and there are metals. In P block, there is non-metals, metalloids, and metals. Right? P block contains so many gases. All these are gases. This is a gas, this is a gas, this is a gas, this is a gas, this is a gas. While, this is the liquid, this is the liquid. One and only liquid non-metal, bromine. One and only liquid non-metal, bromine. And one and only liquid metal, mercury. There are two liquid elements in the periodic table at room temperature. Bromine, non-metal liquid, and mercury, metal liquid. Gallium can be in the liquid state in a reasonably hot day because the melting point is too small. But we don't consider as a liquid element in the normal condition. This is a review about the long periodic table. And that is what explained in the textbook, which you can see. And there is a talk on, this is almost over, the idea of naming elements above 100. How to name the systematic name of elements above 100. That is there in the NCERT. Even last year Neet exam, there was a question. What is the systematic IUPAC name of element 119? What is the systematic IUPAC name of element 119? 119. How to name it? How to name it? It's based on the nature of the digits. 0, it is nil. 0, it is nil. I think now it is visible almost. 0, nil, then un, bi, tri, quad, pent, hex, sept, 7 for sept, oct, n. This is the kind of naming for the digits. Now we were talking about, as I said, the last Neet exam question 119. How do we name it as? 1 is un. It is un. Un, symbol is u. Then again 1, un. Then 9. 9 stands for n. E, u, u, e. It is un, ennium. Un, ennium. Right? There can be questions again based on the systematic IUPAC name. But I feel like the chances are less because almost all elements, their names are declared by IUPAC and is there in the NCERT book itself. But again, there is a possibility. They may ask, as the content is there in NCERT, regarding the systematic IUPAC name of elements based on the name of that digits. For example, 115. How do we name it? 115. 115. How it is 115? Pentium. Pentium. 118. 118. Octium, which is organoson. OG. The name is already available. The name is already approved and there in the text. Right? 118. 118. Octium. So that also, please don't forget to go through the systematic naming of elements. IUPAC system of naming from atomic number 100 onwards. Electronic configuration and all, already I have explained. Electronic configuration of the various group of elements already I have explained. This was an old question. Atomic number 120 have not discovered. If discovered, where the position will be? Old neat question. Atomic number 120, if discovered, in which group it will be? Very simple. 118 already available, noble gases, organoson, 118. After noble gases, then we are going to continue from alkali metal, 119, alkali metal group 1 and 120, group 2, alkaline earth metal. That was a previous question. Group 2, alkaline earth metal. That is about the periodic table classification. Now we are going to start the actual periodicity discussion. Actual periodicity discussion starts now from atomic radius. From atomic radius. Atomic radius is explained on several grounds. Atomic radius is explained on several grounds. Number one, it is ionic radius. Number one, ionic radius. Imagine we are dealing with ionic substances like NaCl, KCl, etc. We will be talking about ionic radius. When we are talking about ionic solids, we talk about ionic radius. So ionic radius can be intended for ionic substances, cation, anion involving substances. There is covalent radius. Covalent radius. Covalent radius is meant for atoms which are covalently bonded. For example, if you are talking about Cl2, Cl2, you know it is ClCl. Two chlorine atoms are bonded like this. It is the half the internuclear distance that is called the covalent radius. This is called the covalent radius. Half the internuclear distance that is called the covalent radius in a bonded situation. In a bonded situation that is called the covalent radius. So ionic radius for ionic substances, covalent radius for covalently bonded atoms giving their molecules. Then there is another one, metallic radius. Metallic radius. Metallic radius meant for metals. For all metals where atoms are arranged in a crystallographic system, metallic radius we can take into consideration. So ionic substances you can take ionic radius. Covalently bonded atoms giving their molecules you can take covalent radius. In metals we can take metallic radius. For gaseous molecules there is another one, van der Waals radius. You might have heard about van der Waals radius. Van der Waals radius we take for gaseous system. Van der Waals radius. What is van der Waals radius? Van der Waals radius means, imagine we are talking about helium molecules. You know helium molecules are monoatomic. So this is one molecule of helium and this is another molecule of helium. You take the distance between the two neighboring molecules and take the half of that. That is van der Waals radius. This is one helium molecule. Helium is monatomic. This is another helium molecule. Helium is monatomic. And the two gaseous molecules slightly far apart, you know, they have a limitation to come close, right? And they will be slightly separated. You take the distance between the two molecules, molecular nuclei, and take the half of that. That is called the van der Waals radius. Even For diatomic molecules, you can consider van der Waals radius. Imagine we are taking two chlorine molecules. This is one chlorine molecule and this is nearby another chlorine molecule. This is one chlorine molecule and this is nearby another chlorine molecule. Already we have discussed this distance, half of that is called the covalent radius. That is covalent radius. Suppose you take the distance between these two nuclei and take the half of that. That is called the van der Waals radius. Always van der Waals radius will be larger value. If you see the size of noble gases, you can see higher value. Because for noble gases, monoatomic noble gases, we can consider only van der Waals radius. Whenever you take van der Waals radius, when you compare with the covalent radius, it comes almost double. Right? This is the various atomic radius parameters we consider. Ionic radius, covalent radius, metallic radius, van der Waals radius. Right? Now about the periodic trend. You know what is the periodic trend? That's a general famous point. As you go down the group, atomic size increases. As you go down the group, atomic size increases. Because going down the group, new shells are added, the size of atom increases. So down the group, atomic size increases. Across the period, the atomic size decreases. Because across the period, there is an increase in nuclear charge. The number of shells remain the same. The increase in nuclear charge causes decrease in atomic size. So what is the general trend? What is the general trend of atomic size? Down the group, atomic size increases. Down the group, atomic size increases. While across the period, atomic size decreases. That is the general trend what we can see. Is it okay we simply see the general trend? No. That you come to know when you go through the NCERT text. If you go through NCERT text referring the atomic size, you can find several tabulated data given. Moreover, there are certain graphical plots given which you must go through in detail. Look at the comparison of graphical plot which you need to have a meticulous idea. You should have a meticulous idea regarding this comparison. You see, group 1 alkali, second series elements are given in the first plot here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. This is first series element. I mean second series, second period, first series of every family. First member of every family. Second period element, lithium, beryllium. This you see the meticulous analysis. We know across the period size decreases. We must know exactly how it decreases. You see the difference between lithium, beryllium, very large difference. Beryllium, boron, that difference decreases. Boron, carbon, carbon, nitrogen, nitrogen, oxygen, oxygen, fluorine. So you should have a meticulous idea regarding such data and graphical representation that is given in the NCERT. What we generally comment, going across the period, size decreases. How it decreases? Somewhat like this it is decreasing. Hope you understand. Now, going down the group, atomic size increases. We say going down the group, atomic size increases. Is that general comment is enough? I would say no. Why? Look at alkali metal, going down the group, atomic size increases. Is it simply increasing? No. Lithium, sodium, potassium, there is a rapid increase. While from potassium to cesium, the increase is almost regular. So that kind of meticulous analysis we need to have based on NCERT, because whatever given in NCERT, you can expect a question. Okay. Look at the halogens. Who look at halogens, down the group size increases. How it is increasing? Fluorine, chlorine increase is more rapid. While chlorine, bromine, iodine, it's a regular increase. So kindly go through the each and every minute aspect that is quoted in the textbook. This is first periodic property regarding atomic size. Okay. I hope that is clear. When you go through atomic size, you must be very careful handling some questions like this. suppose they give you elements like or species like X, X plus, X minus, and element X forming cation and anion. How will you arrange the atomic size? Very simple. A cation will be smaller than neutral atom, while anion will be larger than neutral atom. So it will be X plus, X, X minus. Such kind of questions you can expect. While there is another very important kind of question for isoelectronic species. Suppose they give you some isoelectronic species. Imagine they are giving some isoelectronic species. Sodium plus, oxygen 2 minus, fluorine minus, N3 minus. Then aluminium 3 plus. Then magnesium 2 plus. All these are isoelectronic species. What is isoelectronic species? Same number of electrons. Sodium atomic number 11 minus 1, 10 electrons. Oxygen atomic number 8 plus 2, 10 electrons. Fluorine atomic number 9 plus 1, 10 electrons. Nitrogen 7 plus 3, 10 electrons. Aluminium 13 minus 3, 10 electrons. Magnesium 12 minus 2, 10 electron. All these are containing same number of electrons. If there is a comparison asked, how is the size? I think all of you know, majority of you know how to answer it. Cations will be smaller, anions will be larger. Cation with high positive charge will be very small. Anion with high negative charge will be larger in size. So which is the smallest one? Which is the smallest one in the list? This will be smallest. So it is aluminium 3 plus minimum. Then Mg2 plus next. Then sodium plus next. Then F minus. Then O2 minus. Then N3 minus. This will be the order of their arrangement. So atomic size of the size of species, isoelectronic species, it will be based on their effective nuclear charge. Here the nuclear charge is 13 proton. Here the nuclear charge is 12 proton. Here the nuclear charge is 11 proton. Here it is 9, here it is 8, here it is 7. So according to the nuclear charge, there is a greater nuclear charge, size will decrease. Very, very important idea. So this kind of observation has to be done based on the first periodic property, atomic size. What comes as a second periodic property? It is very important, ionization enthalpy. What is ionization enthalpy? It is the energy required to remove the most loosely bound electron from an isolated gaseous atom. That is ionization enthalpy. Ionization enthalpy. Ionization enthalpy, delta HI. This is delta HI, ionization enthalpy. If you take M, an element M in the gaseous state, converted to M plus gas, releasing an electron, and this is called delta HI1, first ionization enthalpy. Ionization enthalpy is defined as the energy required to remove the most loosely bound electron from an isolated gaseous atom. This is ionization enthalpy. All of you know ionization enthalpy depends on various factors. Various factors, mainly size of the atom, electronic configuration, effective nuclear charge. Many parameters influences ionization enthalpy. Quite naturally, alkali metals have low ionization enthalpy. Noble gases are having very high ionization enthalpy. All of you know. And as we go across from left to right, ionization enthalpy increases. As we come down the group, ionization enthalpy decreases. We know this. It is mainly influenced by size and many other parameters like electronic configuration, etc. Right? So removal of last electron, that is first ionization enthalpy, removal of one more electron, that is called a second ionization enthalpy. Removal of one more electron, that is called a third ionization enthalpy. So first ionization enthalpy, second ionization enthalpy, third ionization enthalpy. I don't have to tell you, the value keep on increasing. Delta HI1 is less than delta HI2 less than delta HI3, so on. The subsequent ionization enthalpy keep on increasing drastically. I remember one question, more than once it came. One question came in such a way, an element having their IE value 1, 2, 3, 4, 5 given in such a way that IE value first one, it is given, say, for example, 2.4 electron volt. Second value given some 3.8 electron volt. Third value it is given some 6.9 electron volt. Fourth value given some 25.2 electron volt. Fifth value given some 30.5 electron volt, like that. Such data given. I don't remember the exact data. I'm speaking the content and concept of the question which came previously. Such data given, and they ask you, how many valence electrons are possible for this element M? If you are intelligent enough, you can easily find out. The answer is 3. You see, removing the last electron, energy required is 2.4. Removing the next electron, energy required is 3.8. Look at the difference. Removing the next electron, energy required is 6.9. Look at the difference. So difference between 1 and 2, very small. Difference between 2 and 3, not much. What about the difference between 3 and 4? What is the difference between 3 and 4? It's a large jump. From 6.9 it is jumping to 25. There is a huge jump between 3 and 4. That means the fourth electron is available in the inner core. That means 3 electrons are available in the valence shell. That was the question. Such beautiful kind of simple questions, simple logical questions, you must be able to prepare handling this kind of area. Okay. So that is about ionization enthalpy. Once again, you need to have a meticulous analysis of the trend that is explained in the textbook. Let us see some graphical or something like that it is given. Yes, we have a graph. We have a graph explaining the ionization enthalpy versus atomic number. Starting from, say, hydrogen, helium, you see it goes like that. Hydrogen, helium, lithium, beryllium, it goes like that. In this graph itself was one question earlier. This graph itself was one question earlier. A fractional segment of this graph was given, and they have given A, B, C, D, E, F. Ask you, what is this A, B, C, D, E? You can see on the peaks you have noble gases. You see that? On the peaks, you have noble gases. They have very high ionization enthalpy because they have a closed filled electronic configuration. Noble gases are having closed filled electronic configuration. Not easy to remove their electron. You can't easily ionize them. Their ionization enthalpy is very high. The highest ionization enthalpy in the periodic table, helium. While alkali metals are available at the bottom. Alkali metals are available at the bottom. You see the alkali metals which are available at the bottom. For alkali metals, ionization enthalpy is low value. For noble gases, ionization enthalpies are high value. Matter is very simple. But if you haven't gone through this type of graphical analysis, you may fail sometimes answering the direct questions even. Or you may commit a mistake at least. Okay. And remember, always ionization enthalpy is represented in kilojoule per mole. There is a definite unit for ionization enthalpy. It is kilojoule per mole. That is a unit of ionization enthalpy, right? Is there any other graph? Yes, there are graph. This is a very important graph, I would say. This is a very important graph. Look at the graph. That is for the second series, second period elements. Lithium, beryllium. You can see lithium. See, from lithium to right, the ionization enthalpy increases, but not regularly. There is a irregular trend between beryllium boron. Beryllium greater than boron. There is a irregular trend between nitrogen and oxygen. Nitrogen greater than oxygen. Many of you know the reason. From left to right, ionization enthalpy increases. Is it regular trend? No. Between beryllium boron, there is abnormality. Between nitrogen oxygen, there is abnormality. Why? Some of you definitely know why. Suppose we are taking up beryllium and boron. Beryllium having configuration 4 electrons, 1s2, 2s2. Boron 5 electron, it is 1s2, 2s2, 2p1. Here the last electron you are removing from s orbital. Here the last electron you are removing from p orbital. Removing electron from p orbital is much easier than removing electron from more compact s orbital. S orbital is more compact in nature. So it is easy to remove electron from here than here. So the value for boron will be lower than beryllium. What about nitrogen and oxygen? That is much more famous, maybe known to more people. Between nitrogen and oxygen, nitrogen having 2s2, 2p3 configuration, oxygen having 2s2, 2p4 configuration, and the point lies here. Already you might have got the idea. P3 configuration has got something special. P3 configuration is extra stable due to half-filled configuration. So P3 configuration, which comes out like this, exactly half-filled, and P4 configuration, it is unsymmetric system. This is P4 configuration. So extra stability of half-filled configuration make nitrogen to have higher ionization enthalpy, where oxygen, unsymmetric electronic system, makes easy to remove electron comparatively. So oxygen has got a lower ionization enthalpy than nitrogen due to this fact. So those things we must be very, very careful. Okay. So that is about ionization enthalpy. So atomic size, trend number 1. At ionization enthalpy, trend number 2. Periodic trend number 2. There is a topic regarding shielding effect, screening effect. Shielding effect, screening effect. What is meant by shielding effect? Shielding effect means the control of nucleus to the valence shell is governed by intervening orbitals. The control of nucleus to the valence shell is controlled by intervening orbitals. When the intervening orbitals increases, due to their screening effect, the control of nucleus to the valence shell will decrease. This is called a screening effect. And the screening effect is maximum given by s orbital, then p orbital, while d and f orbitals are having poor screening effect. So the order of screening power comes out to be in the order screening power. Screening power comes out to be S greater than P greater than D, F. D and F orbitals are having poor screening effect. So suppose intervening orbitals more S and P orbital, control of nucleus to the valence shell will decrease. Suppose intervening orbital coming D and F orbital, their screening power is minimum. Therefore, control of nucleus to the valence shell will be more than what we expect. That is called a poor screening effect. And the reason for lanthanoid contraction, earlier we were referring, it is due to poor shielding effect of, poor screening effect of D and F orbital electrons. Therefore, the atomic size will decrease. One important consequence is lanthanoid contraction. Okay. So such things also you can go through. Another important trend is we are going to discuss electron gain enthalpy. What is meant by electron gain enthalpy? It is the energy involved when an electron is added to an isolated gaseous atom. That is electron gain enthalpy. Enthalpy change involved. Electron gain enthalpy. We represent delta H E G. Once again, the unit is kilojoule per mole. What is electron gain enthalpy? X, a neutral gaseous atom, added with an electron, you get a X minus gas. And the energy involved is called electron gain enthalpy. It is the enthalpy change when an electron is added to an isolated gaseous atom giving an anion. This is electron gain enthalpy. Almost all elements in the periodic table, electron gain enthalpy is negative. And we call it as negative electron gain enthalpy. While a few elements like noble gases are having positive electron gain enthalpy. And elements like nitrogen having positive electron gain enthalpy. A few elements are having positive electron gain enthalpy. Almost all elements are having negative electron gain enthalpy. High negative electron gain enthalpy is shown by, this is a very important table you must go through. The high negative electron gain enthalpy is shown by halogens. Halogens perform high negative electron gain enthalpy. You can see the halogens, especially chlorine. Chlorine is the element in the periodic table showing maximum negative electron gain enthalpy. Because we know they have a great tendency to accept electron. So they accept electron and get stabilized by losing energy. So when chlorine accepts one electron, giving Cl minus, the energy released is minus 349 kilojoule per mole. That is the highest negative electron gain enthalpy. Second place goes to fluorine. Third place to bromine. Fourth place to iodine. And then astatine. While oxygen family coming only second. And that too, oxygen is much below. Oxygen is much below. The kind of abnormality what you get chlorine. Why fluorine is lower value than chlorine? Why fluorine getting a lower negative electron gain enthalpy than chlorine? The reason is very simple. Because of small size of fluorine. Due to small size of fluorine, chlorine is much larger. Due to small size of fluorine, there is interelectronic repulsion. That could be the reason why fluorine is having slightly lesser value compared to chlorine. Chlorine 349, fluorine minus 328. Such a observation we can find here also. Sulfur having greater value of negative electron gain enthalpy. Oxygen having a lower value. And here, chlorine, after chlorine it is fluorine. Here, after sulfur it is not oxygen. After sulfur it is selenium. After selenium, it is tellurium. After tellurium, it is polonium. And only last oxygen is coming. Some interesting observations which you need to note down from the textbook. While you see alkali metals, hydrogen alkali metals, they are having very low negative electron gain enthalpy. While noble gases are having positive electron gain enthalpy. Noble gases are having positive electron gain enthalpy. That too, neon, high positive. High positive shown by neon. So this kind of observations, a thorough look at the data-wise analysis. I'm not telling you to memorize the data, but we need to know specifically who is maximum, who is second, who is third, who is minimum. What kind of order it can be. Any sort of abnormal characters we must go through. This is regarding electron gain enthalpy. Electron gain enthalpy. Traditionally, we have a term used, electron affinity. Electron affinity. Electron affinity is a more general term. Electron gain enthalpy is correct thermodynamic expression. Electron affinity, we simply say a chlorine having high electron affinity. The high negative electron gain enthalpy, high electron affinity. So what about high positive electron gain enthalpy? It is negative electron affinity. We don't call negative electron affinity, rather we call zero electron affinity. Noble gases are having zero electron affinity. Actually it is negative electron affinity, but we don't use that term, zero electron affinity. Electron affinity is another conjugated term which earlier many books and even now it is used in explaining the phenomenon connected to adding electron to a neutral atom. So from a neutral atom, electrons are removed, it is ionization enthalpy. To a neutral atom, if electrons are added, it is called electron gain enthalpy. So atomic size, trend number 1. Ionization enthalpy, trend number 2. Electron gain enthalpy, trend number 3. What next is another very important thing, electronegativity. Electronegativity. Regarding electronegativity, it is not the property of an isolated atom. Ionization enthalpy is the property of an isolated atom. Electron gain enthalpy is the property of an isolated atom, while electronegativity is not the property of an isolated atom. It is the property of an atom in a bonded condition. It is a varying property. It is not an absolute value. It is referring to the tendency of an atom to attract the shared electron towards it in a covalent bond. That is what called electronegativity. Electronegativity is not a measurable quantity. It is not a measurable quantity. Electronegativity. That is only a relative quantity. It was explained by many units, Pauling scale, Mulliken-Jaffe scale, Aldred-Rochow scale. We consider mainly Pauling scale. And the reference is the most electronegative element in the periodic table, fluorine. That is the reference. Fluorine is the most electronegative element in the periodic table. And that is the reference having highest electronegativity 4 units in Pauling scale. Generally in the NCERT, the electronegativity unit we are using is Pauling scale electronegativity. So fluorine, the most electronegative. The second most is oxygen. The third most is almost equal nitrogen and chlorine. But the effect is greater for nitrogen because of smaller size. Chlorine is larger in size. So most electronegative, super halogen, fluorine. Second most, oxygen. Third, nitrogen and chlorine. But the effect is an upper hand for nitrogen due to small size. And what about the trend of electronegativity? What is the trend of electronegativity? Electronegativity decreases down the group and increases across the period. Electronegativity decreases down the group, increases across the period. We have a periodic trend of explanation for many periodic property explained as a diagram here. Explained as a diagram here in the text. You see, electron gain enthalpy increasing from left to right across the period. Ionization enthalpy increases from left to right across the period. Electronegativity increases from bottom to top. Atomic radius increases from top to bottom. Non-metallic character diagonally upward increasing. Metallic character diagonally downward increasing. Ionization enthalpy increases from bottom to top. Electron gain enthalpy increases from bottom to top. Electron gain enthalpy means negative electron gain enthalpy. Okay. But still there are exemptions. If you take fluorine, chlorine is greater than fluorine. Like that. Atomic radius increases from left to right to left. Electronegativity increases from left to right. So many such a trend we can get graphically represented or diagrammatically represented in the textbook. Is it clear? So some important periodic trend if you go through electronic configuration, very, very important. atomic radius, very, very important. Electron ionization enthalpy, electron gain enthalpy, electron negativity. Right? Yes. What else? What else in the chapter? Now, there is a talk on periodicity of valence or oxidation state. Valence electrons, oxidation state. That's a very important point. First of all, let me tell you what is meant by valence, what is meant by valence electrons. Valence means combining ability. Valence means combining ability. Valence electrons means number of electrons in the valence shell. Right? If you talk about magnesium and oxygen, say for example, if you talk about magnesium and oxygen, say for example, for magnesium, it is group 2 element, the number of valence electron equal to 2 and valency is also equal to 2. Magnesium is a divalent species. How many valence electrons? Valence electron means number of electrons in the outermost shell. It is 2 electron. All of you know magnesium atomic number 12. It is 2, 8, 2. 1s2, 2s2, 2p6, 3s2. This is the configuration for magnesium. Valence electron, 2 valence electron. What is the valency? 2. So valence electrons and valency remain the same. But if you go to oxygen from 16th group, oxygen atomic number 8, it is 1s2, 2s2, 2p4. This is the configuration and number of valence electron. It is 8 electron means 2 and 6. It is 6 valence electron. Number of valence electron equal to 6. What is the combining ability? What is the valency? All of you know what is the valency of oxygen. Valency of oxygen is 2. How is that? It is able to accept 2 electron. Magnesium loses 2 electron, valency 2. Oxygen in the valence shell there are 6 electron. So it is ready to accept 2 electron to make it octet. And again valency is 2. Valence electron is 6, valency is 2. So what is meant by valence electrons and valency? Many times valence electron and valency are same. Many times valence electrons and valency are different. Right? If you go to non-metals, valency will be 8 minus valence electron. If you go to non-metals, right hand side of the periodic table, valency will be 8 minus valence electrons. Right? So combining ability can be well explained by combining with the combination with the hydrogen. If you take group 1, for example, sodium hydride, it is monovalent. If you take group 2, it is calcium hydride, it is divalent. If you go to group 13, aluminium hydride, it is trivalent. If you go to group 14, methane, tetravalent. If you go to group 15, ammonia, it is trivalent. So valency gradually increasing from 1 to 4 and then decreases. 1, 2, 3, 4, 3. What about 16? Oxygen family, H2O, it is divalent. 17 halogens, HCl, monovalent. See how it is the trend coming? It is 1, 2, 3, 4, 3, 2, 1. Such a trend we can find. So valency means combining ability. Valence electrons means number of electrons in the valence shell. Many times valency and oxidation state are same, but not always. Not always. If you take a valency and oxidation state, I'll tell you a very simple example to understand the difference between the two. You see, I'm taking aluminium chloride. The valency is 3. Aluminium combining with 3 chlorine. The valency is 3. What is oxidation state? Chlorine minus 1 into 3 minus 3, aluminium 3 plus. Oxidation state is also 3. Oxidation state also 3 plus 3 state. See, valency and oxidation states are same if you take AlCl3. What if I am taking another example? What if I am taking another example? Say AlH2O 6 times Cl3. Suppose I am taking a complex formula AlH2O 6 times Cl3. What is the valency of aluminium? What is the valency of aluminium? The valency of aluminium, you see, aluminium is bonded to 6 water molecules. You know coordination molecules. Water molecule number 1, water molecule number 2, water molecule number 3, water molecule number 4, water molecule number 5, water molecule number 6. Here valency is 6. Here covalency is 6. But what is the oxidation state? Water molecule is neutral. Chlorine minus 1 into 3 minus 3. Aluminium 3 plus. You see, oxidation state is plus 3. Oxidation state is plus 3. But valency is 6. So not necessarily always covalency and oxidation state coming same. Here oxidation state and covalency are same. Plus 3 and trivalent. Here oxidation state is plus 3, but it is hexa-coordinated. It is making a covalency 6. This is very important to understand in that context. When we refer to oxidation state, it is interesting to see the trend with oxides. Trend with oxides we can interestingly find out. The trend with oxides. How the trend with oxides is coming? Group 1, sodium monoxide. Group 2, calcium oxide. Group 13, aluminium oxide. Group 14, carbon dioxide. Group 15, nitrogen pentoxide. Group 16, sulfur trioxide. Group 17, chlorine heptoxide. How is the oxidation number coming? Sodium monovalent, calcium divalent, aluminium trivalent, carbon plus 4 oxidation state, nitrogen plus 5 oxidation state, sulfur plus 6 oxidation state, chlorine plus 7 oxidation state. Oxygen is minus 2 into 7, or this 7 comes here, 2 here, comes here. Minus 2 into 3 minus 6 plus 6, and 5 comes here, 2 minus comes here. Minus 2 into 2 minus 4 plus 4. 3 comes here, 2 minus comes here. This is 2 minus 2 plus. This is minus 1, this is plus 1. You see the trend from group 1 to 17. Oxidation number 1, 2, 3, 4, 5, 6, 7, like that. Trend of oxidation state. So trend of valency with reference to hydrogen, trend of oxidation state with reference to oxygen, oxides. These are some important points to remember from the chapter. While a conclusion portion I would like to discuss from the chapter is another important area regarding nature of oxides. Nature of oxides. It is always better to prepare a tabulated form regarding the nature of oxides. Nature of oxides. There are mainly basic oxides. There are acidic oxides. There are neutral oxides. And there are amphoteric oxides. It is better to make a tabulation like this, because many times in the other chapters also we encounter a variety of examples. Knowing the facts and figures of various oxides and their character is very, very important. If you take a strong metallic oxide, it is basic in nature. Sodium oxide, basic in nature. Magnesium oxide, basic in nature. Calcium oxide, basic in nature. So many metal oxides are basic in nature. While oxides of electronegative elements, oxides of non-metals are acidic in nature. Carbon dioxide is acidic in nature. Cl2O7 is strongly acidic in nature. N2O5 is acidic in nature. SO3 is acidic in nature. SO2 is acidic in nature. So knowing a fact and figure about this character is very, very important. Sir, how do we say acidic basic? Very simple, children. Very, very simple. If you take calcium oxide, when treated with water, you are getting calcium hydroxide. This is alkaline basic. That's why it is called basic. If you take Cl2O7, when treated with water, you are getting a strong acid. HClO4, perchloric acid. That's why it is called acid. If you take sulfur trioxide, treated with water, you are getting strong sulfuric acid. That's why it is called acidic. So basic oxide means basic. Acidic oxide means giving acids. What about neutral? Neutral oxides. They are neither acidic nor basic. Neither acidic nor basic. Carbon monoxide, neutral. Nitric oxide, neutral. Nitrous oxide, neutral. We should learn this. Wherever we get informations, we should update in the table and go through that. I'm sure in every competitive exam, 1 or 2 questions you will be able to answer. What is amphoteric? All of you know what is amphoteric. Amphoteric means the one which acts as both acidic and basic. Both acidic and basic. Amphoteric. Right? For example, amphoteric oxide. Aluminium oxide is amphoteric. Zinc oxide is amphoteric. Beryllium oxide, it's a quite interesting thing. Beryllium fall under alkaline earth metal, but it is amphoteric in nature. Beryllium, suppose somebody asks you, what are alkaline earth metals? What are alkaline earth metals? Choice 1, beryllium, magnesium, calcium, strontium, barium, radium. Of course, let us omit radium, radioactive. Suppose this is choice 1 given to you, another choice given to you, magnesium, calcium, strontium, barium. Which is alkaline earth metal? Your answer should be second one. Because beryllium is out of the definition of alkaline earth metal because it is amphoteric in nature. It is not alkaline, it is amphoteric in nature. Aluminium oxide is amphoteric in nature. Zinc oxide is amphoteric in nature. Tin, lead oxides are amphoteric in nature. So there are variety of oxides. Basic oxide, the one which gives bases. Acidic oxides, the one which give acids. Neutral oxides, neither acidic nor basic. Amphoteric oxides, both acid and base. With a strong acid, it will act as a base. With a strong base, it will act as an acid. That probably is the last content from the chapter. Right? These are the important points which you need to learn from this small chapter. Let me rewind. We started from the historical aspects of periodic table. What are the various historical aspects which we have gone through? Then modern periodic law. Moseley's contribution, periodic table arrangement, groups and periods, various things. Then electronic configuration, S block, P block, D block, F block, electronic configuration, atomic radius, atomic size, ionization enthalpy, electron gain enthalpy, electronegativity, various trend, valency, valence electrons, oxidation state, and finally nature of oxides. Right? That's about the short chapter, small chapter, chapter 3, classification of elements. We'll meet in another class, another video with another quick revision of another chapter. Okay? Till then, bye. See you. Take care.